Welcome to this video on problem number 23, merge k-sorted lists. This is a classic problem that tests your understanding of linked lists and efficient merging strategies. We'll explore various approaches to solving this problem, analyze their complexities, and discuss the trade-offs involved. Let's dive in. In this problem, we are tasked with merging multiple sorted linked lists into a single sorted linked list. The input is an array of k linked lists, where each linked list is already sorted in ascending order. The goal is to combine all these sorted linked lists into one unified linked list, still maintaining the ascending order, and return the head of the merged list. For the input format, the array lists contains the head nodes of these k linked lists. Each node in a linked list holds an integer value, and if a linked list is empty, its head node will be represented as null. The output of the problem is the head node of the final merged linked list, which will contain all the nodes from the input lists combined in sorted order. In the first example, we are given three linked lists, 1-4-5, 1-3-4, and 2-6. When we merge these lists, we traverse through all the nodes of the linked lists, comparing their values, and arrange them in ascending order. The result is a single sorted linked list, 1-1-2-3-4-4-5-6. In the second example, the input consists of an empty array of linked lists, meaning there are no lists to merge. Therefore, the output is null, as there are no nodes in the final merged list. In the third example, the input array contains three empty linked lists, represented as null, null, null. Since all the lists are empty, there are no nodes to merge, and the output is also null. This highlights a scenario where even if the input contains multiple linked lists, if all of them are empty, the result is an empty merged list. The constraints specify that the number of linked lists, k, can range from 0 to 10,000, and each linked list can contain up to 500 nodes, making it important to consider the efficiency of our solution. Additionally, the values of the nodes in the linked lists can range from -10,000 to 10,000, and it is guaranteed that each linked list is already sorted in ascending order. Some critical edge cases to consider include when the input list is entirely empty, where k equals 0, or when all the linked lists in the input are empty, both of which should result in null as the output. If the input contains only one non-empty linked list, the output should simply return that list as is, since no merging is required. Finally, the solution must handle large inputs efficiently, ensuring that it can manage up to 10,000 linked lists and their combined nodes without performance issues. When considering how to merge k-sorted linked lists, the brute force approach is the simplest to understand but not the most efficient. The idea is to gather all the elements from the k lists, store them in an array, and then sort the array. Once sorted, we can reconstruct the merged linked list by iterating through the sorted values. This approach has a time complexity of n*log n, where n is the total number of nodes across all the lists. The sorting step dominates this complexity. While this method is straightforward and easy to implement, it doesn't take advantage of the fact that the individual lists are already sorted. As a result, it introduces unnecessary overhead, making it suboptimal for this problem. An alternative strategy is pairwise merging, where we merge two lists at a time until all k lists are merged into one. This method leverages the merge step from the merge sort algorithm. We start by merging the first two lists, then use the result to merge with the next list, and so on, repeating this process until we have a single merged list. The time complexity for this approach is k*n, because each merge step processes all nodes in the lists being merged, and we perform k-merge operations. While this approach is more efficient than brute force in avoiding unnecessary sorting, it becomes inefficient when k is large because merging sequentially introduces redundant operations. However, it does have the benefit of using extra space, as the merging is done in place. To address the inefficiencies of pairwise merging, we can use a divide and conquer strategy. This approach splits the k-lists into pairs, merges each pair recursively, and combines the results until only one sorted list remains. By breaking the problem into smaller, more manageable parts, we reduce the number of redundant merging steps. This strategy has a time complexity of n*log k, because there are log k levels of merging, with each level processing all n nodes. The space complexity remains O1 for in-place merging. This method is efficient and leverages the sorted nature of the lists, making it a strong candidate for large-scale scenarios. However, the implementation can be slightly more complex compared to simpler approaches like brute force. Another highly efficient method is to use a min-heap or priority queue. This approach tracks the smallest element across all k lists by maintaining a heap of the first node from each list. The algorithm repeatedly extracts the smallest node from the heap, adds it to the merged list, and then pushes the next node from the same list into the heap. This process continues until the heap is empty. The time complexity is O(n*log k, because each insertion or extraction from the heap takes O(log k), and we perform these operations for all n nodes. The space complexity is O(k) to store the heap. This method is particularly efficient for large K due to its logarithmic scaling and is easy to implement using built-in heap libraries. However, it does require additional space for the heap, which is a trade-off for its performance. Among the approaches discussed, the min-heap or priority queue method is the most balanced in terms of time complexity and ease of implementation. With a time complexity of O(n*log k, it matches the efficiency of the divide-and-conquer approach. However, it stands out for its intuitive design, leveraging built-in libraries to simplify implementation. This method is well suited for merging sorted lists because it ensures that at each step, the smallest available element is added to the merged list, maintaining the sorted order. While the brute force approach is too inefficient due to unnecessary sorting, and pairwise merging suffers from redundant operations for large K, the heap-based strategy minimizes these inefficiencies. For most practical scenarios, the trade-off between time complexity and space usage makes the min-heap approach the clear choice for merging K-sorted lists efficiently. In this problem, we are given multiple sorted linked lists, and the task is to merge all these lists into one single sorted linked list. Each individual linked list is already sorted in non-decreasing order, so our goal is to combine all their elements into a single list that preserves this order. The approach we'll focus on here is a brute force method. The idea is to break the problem into two main steps. First, extract all the node values from the given linked lists into a flat array, and second, sort this array and use it to reconstruct the final sorted linked list. While this method is straightforward and easy to implement, it prioritizes simplicity over efficiency, as we'll see in the detailed steps ahead. The brute force algorithm begins with the extraction of all node values from the linked lists. To do this, we initialize an empty array called values. Then, for each of the K linked lists, we traverse through all their nodes one by one, appending the value of each node to the values array. Once we've processed all K linked lists, this array will contain all the node values from all the lists combined. For example, if the input linked lists are list 1 with values 1, 4, 5, list 2 with values 1, 3, 4, and list 3 with values 2, 6, the resulting array after this step will be 1, 4, 5, 1, 3, 4, 2, 6. Next, we sort this array in non-decreasing order using a sorting algorithm like quicksort or mergesort. After sorting, this array will contain all the values in sorted order, making it ready for the final step of reconstructing the linked list. After sorting the array, we proceed to reconstruct the merged sorted linked list. To do this, we create a dummy node that serves as the starting point of the new linked list. We also initialize a pointer, current, to this dummy node. Then, for each value in the sorted array, we create a new linked list node and link it to the current node by updating its next pointer. We move the current pointer to the newly created node after each insertion. Once we've processed all the values in the array, the dummy node's next pointer will point to the head of the fully constructed sorted linked list. For example, if the sorted array is 1, 1, 2, 3, 4, 4, 5, 6, the resulting linked list will be 1-1-2-3-4-4-5-6. Finally, we return dummy.next as the head of this sorted linked list. This approach offers several key insights. First, using an array to store all node values simplifies the sorting process. Most efficient sorting algorithms, such as quicksort or mergesort, are designed to operate on arrays, making this step straightforward. However, the sorting itself is the most computationally expensive part of the algorithm, with a time complexity of O(n*log n, where n is the total number of nodes across all K linked lists. It's also important to consider edge cases. If all the input lists are empty, the output is simply an empty list. If there's only one list, the output is the same as the input list, and if the lists have varying lengths, the algorithm handles this naturally by iterating through all nodes. Finally, while this approach is conceptually simple, it uses additional memory to store the intermediate array, which makes it less space efficient compared to heap-based methods. The brute force method relies on two primary data structures, arrays and linked lists. The array is used to store all node values before sorting. Its main advantage is that it simplifies the sorting process, as arrays are the natural input for most efficient sorting algorithms. However, the downside is that the array requires additional space proportional to the total number of nodes, which increases the overall memory usage. The linked list, on the other hand, is used to reconstruct the output in the same format as the input. While it maintains the structure of the merged list, the process of reconstructing the list node by node after sorting adds computational overhead. This balance between simplicity and resource usage is a key characteristic of this approach. Finally, let's analyze the time and space complexity of the brute force approach. For time complexity, extracting all the node values into an array takes O(n), where n is the total number of nodes across all k linked lists. Sorting the array is the most expensive step and takes O(n) log n. Reconstructing this sorted linked list from the array takes another O(n), leading to an overall time complexity of O(n) log n. As for space complexity, the array used to store the node values requires O(n) additional space. Reconstructing the linked list is done in place, so it uses O(1) space. Therefore, the overall space complexity is O(n). While the simplicity of this method makes it appealing for smaller inputs, it may not be the most efficient choice for very large k or n due to the additional memory usage and sorting overhead. To implement the solution for merging k-sorted linked lists, we start by importing the heap push and heap pop functions from Python's Heap module. These functions help us manage a min heap, which is essential for efficiently retrieving the smallest element across multiple lists. Next, we define a list node class, which represents a node in a linked list. Each node contains a value and a reference to the next node. Then, we define the mergeKLists method inside the solution class. The method takes a list of linked lists as input. First, we initialize an empty min heap. The heap will store tuples of the form value list index node, where value is the node's value. List index helps us keep track of which list the node belongs to, and node is the actual node object. We then iterate over each list in the input. If the list is not empty, we push its first node into the min heap using heap push. This ensures that the smallest node from each list is added to the heap. To simplify the construction of the merged result, we initialize a dummy node. The current pointer starts at this dummy node and will help us build the merged linked list step by step. Finally, we enter a while loop that continues as long as the heap is not empty. Inside the loop, we pop the smallest node from the heap using heap pop. The value of this node, along with its corresponding list index and node reference, are extracted. The current .next pointer is then updated to point to the smallest node, and we move the current pointer forward to this node. If the node we just added to the merged list has a next node in its original list, we push this next node back into the min heap. This ensures that the heap always contains the next smallest node from the remaining parts of the lists. The process continues until the heap is empty, meaning we've processed all nodes from all the input lists. After the loop finishes, the merged linked list is fully constructed, starting from the dummy node's next pointer. Finally, we return dummy.next as the head of the merged list. This implementation efficiently merges the k-sorted linked lists by leveraging the min heap to repeatedly extract and process the smallest node at each step. The heap ensures that we perform these operations in logarithmic time relative to the number of lists, making the solution both elegant and optimal. To solve the problem of merging k-sorted linked lists in Java, we start by defining the list node class, which represents each node in the linked list. Each node contains an integer value and a reference to the next node. The mergeKLists method is defined in the solution class, which takes an array of list node objects as input. The first step in the method is to initialize a priority queue, or min heap, to store the nodes based on their values in ascending order. This ensures that we can efficiently extract the smallest node at any point. Next, we iterate through the input array of linked lists, adding the head of each non-empty list to the min heap. This sets up the heap with the smallest elements from each list, which will serve as the starting point for our merged linked list. A dummy node is also created to simplify the construction of the result list, and a pointer, current, is initialized to this dummy node to help build the merged list step by step. Once the heap is populated, the algorithm proceeds by repeatedly extracting the smallest node from the heap. This is done using the poll method, which removes and returns the smallest element. The extracted node is added to the result list by setting the next pointer of the current node to this smallest node. The current pointer is then updated to point to this newly added node. If the extracted node has a next node, meaning there are more elements in its original list, the next node is added to the heap. This process continues until the heap is empty, ensuring that all nodes from all k-lists are merged in sorted order. Finally, the merged list is returned, starting from the node after the dummy node, as the dummy was just a placeholder to simplify the merging process. Here, we start with the problem of merging three sorted linked lists. To solve this, we initialize an empty min heap. The min heap will help us efficiently retrieve the smallest element across all lists. First, we push the head node of each list into the heap, along with its value and index. For example, from the first list, we push the node with value 1, from the second list, another node with value 1, and from the third list, a node with value 2. After this initialization step, the heap contains three elements: 1, 0, list node, 1, 1, 1, list node, 1, and 2, 2, list node, 2. Next, we set up a dummy node, which serves as the starting point for our merged list. A pointer called current is used to help us build the merged list step by step. Now, we begin the process of building the merged list. While the heap is not empty, we repeatedly extract the smallest element from the heap. First, we pop the node with value 1 from the first list. This value is added to our merged list by linking it to the current pointer. We then move the current pointer forward. After processing this node, we push the next node from the same list, which has value 4, into the heap. The heap is updated to contain 1, 1, list node, 1, 2, 2, list node, 2, and 4, 0, list node, 4. Next, we pop the node with value 1 from the second list and add it to the merged list. Similarly, its next node, with value 3, is pushed into the heap. The process continues as we pop the node with value 2 from the third list, add it to the merged list, and push its next node, with value 6, into the heap. This process is repeated until the heap is empty, resulting in the final merged list, 1-1-2-3-4-4-5-6. In this example, we handle the edge case of merging two empty lists. Since both lists are empty, there are no nodes to push into the min heap during the initialization step. The heap remains empty throughout the process. As a result, the dummy node, which represents the starting point of the merged list, remains unchanged. This means that the output of this example is simply none, as there are no elements to merge. Here, we consider another case where we are merging a single non-empty list. In the initialization step, we create an empty min heap and then push the head node of the single list into the heap. This node has a value of 1, so the heap now contains 1, 0, list node, 1. With this setup, we move on to building the merged list. The smallest node, which is the only node in the heap, is popped, and its value, 1, is added to the merged list. We then push the next node from the same list, which has a value of 3, into the heap. The heap is updated to contain 3, 0, list node, 3. We continue building the merged list by popping the next smallest node from the heap, which has a value of 3. This value is added to the merged list, and we push the following node from the single list, with a value of 5, into the heap. The heap is updated to contain 5, 0, list node, 5. Finally, we pop the last node from the heap, which has a value of 5, and add it to the merged list. At this point, the heap becomes empty, and the process concludes. The final merged list is 1-3-5. In this problem, we use a min heap to efficiently merge k-sorted linked lists, and the time complexity can be broken down into two main parts. First, during heap initialization, we insert the first node of each of the k-linked lists into the heap. Since each insertion into the heap takes O log k, and we perform this operation k times, the total time for this step is O k asterisk log k. Next, during the merging process, we handle all n nodes across the k-lists. For each node, we perform two heap operations, removing the smallest node, which takes O log k, and inserting its next node, if present, which also takes O log k. Since we process n nodes in total, this step contributes O n asterisk log k. Combining these two steps, the overall time complexity of the solution is O n plus k asterisk log k. Here, n refers to the total number of nodes across all the linked lists, and k is the number of linked lists. Now, for space complexity, we consider the memory required for the heap and the output linked list. The heap stores at most k elements at any given time, as we only keep one node from each list in the heap, resulting in a space requirement of O, k. Additionally, we construct a new output linked list to store the merged result, which requires memory proportional to the total number of nodes, or O, n. Combining these, the total space complexity is O, k, plus O, n, which simplifies to O, n plus k. Let's compare this heap-based approach to a brute force method. In the naive approach, we would concatenate all k lists into one combined list, which would take O, n, time to traverse all nodes. After that, we would sort the combined list, requiring O, n asterisk log n, time. This makes the total time complexity O, n plus n asterisk log n, or simply O, n asterisk log n, which is less efficient than our heap-based solution, especially for larger values of k. The heap-based approach is more efficient because it takes advantage of the fact that the lists are already sorted, reducing the sorting complexity to O log k per node instead of O log n. This makes the heap solution particularly advantageous when k is significantly smaller than n. To analyze the best, average, and worst-case scenarios, let's start with the best case. If k equals 1, meaning there's only one list, no heap operations are required, and the time complexity is simply O, n. In the average case, for typical inputs with k lists and n total nodes, the time complexity is O, n plus k, asterisk log k. For the worst case, where all k lists are roughly the same size, the complexity remains O, n plus k, asterisk log k. This is because heap operations, which dominate the runtime, always cost O log k per node. Mathematically, we see that each of the n nodes is processed exactly once, and each heap operation costs O log k, resulting in O n asterisk log k. The initialization step adds O k asterisk log k, but for large n, this becomes negligible compared to O n asterisk log k. Therefore, the overall complexity remains O n plus k asterisk log k. Here are some common mistakes to watch out for when solving the merge k sorted lists problem. First, forgetting to handle edge cases is a frequent issue. For example, if the input contains an empty list or just one list, your solution should return an empty list or the single list directly. Overlooking these scenarios can cause unnecessary errors. Next, inefficient sorting is another pitfall. If you naively collect all elements and sort them using a typical sorting algorithm, the time complexity becomes O, n log n, where n is the total number of nodes. This can be slow for large inputs and might lead to timeouts. Another mistake is merging lists without leveraging a priority queue. If you iteratively compare the heads of all k lists without using a data structure like a minheap, you end up with an O, n asterisk k, time complexity, which becomes problematic as k grows larger. Additionally, incorrectly managing node references is a subtle but critical issue. When updating the next pointers in your merged list, mishandling them can break the linked list structure, causing cycles or disconnected nodes. Finally, overcomplicating recursive solutions can lead to inefficiencies. In the divide and conquer approach, failing to simplify base cases or reduce the problem size effectively can result in stack overflow or redundant calculations. These are all areas to be mindful of as you refine your solution. Now, let's discuss some useful insights for interviews involving this problem. A key pattern to recognize is that merging k-sorted lists is closely related to merging sorted arrays. Techniques like the two-pointer approach or using a heap are foundational to solving these problems efficiently. Optimization is often a focus during interviews. While a straightforward O, n log n, solution might be acceptable, demonstrating an O, n log k, approach using a heap or divide and conquer shows a deeper understanding of algorithmic efficiency. It's also important to show your awareness of edge cases. Be ready to explain how your solution handles scenarios such as empty lists, lists with varying lengths, or duplicate values. This signals that your solution is robust and well thought out. Additionally, interviewers may ask you to discuss trade-offs. Comparing the time and space complexities of different approaches and justifying why you chose one over another demonstrates a strong grasp of problem-solving strategies. Finally, this problem connects to other related problems, such as LeetCode 21, which focuses on merging two sorted lists, a simpler variation. LeetCode 378, which involves finding the kth smallest element in a sorted matrix, and LeetCode 295, which relies on heap-based optimization to find the median from a data stream, are also worth exploring to deepen your understanding of similar concepts. Let's explore some alternative approaches to solving this problem, each with its own trade-offs. The brute force method involves collecting all elements from the k-lists, sorting them, and reconstructing the merged list. While this approach is straightforward to implement, it's inefficient with a time complexity of n log n, making it unsuitable for larger inputs. A more optimized approach uses a min heap, or priority queue. Here, you maintain a heap of the smallest elements from each list, repeatedly extracting the minimum and adding the next node from the corresponding list back into the heap. This reduces the time complexity to n log k, with a space complexity of k. Another option is the divide and conquer strategy, where you recursively merge pairs of lists until only one remains. This also achieves n log k time complexity and may be more space efficient than the heap approach, depending on the implementation. Lastly, there's iterative pairwise merging, where you merge two lists at a time in a loop until only one list remains. While simpler to implement than divide and conquer, it's less structured and may require more iterations. Each approach has its strengths and weaknesses, so understanding these trade-offs is key to selecting the most suitable strategy based on the problem's constraints and requirements. Great job making it to the end. In this video, we covered the problem of merging k-sorted linked lists, explored multiple approaches, and learned key insights about optimizing for time and space. Remember, consistent practice is the key to mastering coding problems. Thank you for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!